Okay, and 3D characterization of the surface topography. And that is a small tool and a simple tool, but very useful and for a lot of surface like topography. And this involved like 3 different instruments from millimeter scale to the nanometer scale. Okay, we can next slide. We can show this. Here we talk about 3 different tools. The first is called 3D optical microscope, also called like optical profilometer or non-contact or white light interferometer. So this different name, so the same thing. This basically is optical profilometer. And the next I will talk about the stylus profilometer. And okay, that's too quick. So that is this instrument is a stylus profilometer and a contact. So third is like a FM, and also in our lab we have GS in charge of this. And these 3, I will compare that and compare their strengths and weakness. And now next slide, I will talk. Yeah. On the left, that is a picture of the optical profilometer. On the right, you can see this. From the left, the light source. Typically, we use white light, and it goes through a beam splitter. And the 2 way, one is go to the reference mirror, one beam. Another beam go to right on the sample. On the sample, of course, sample is roughness on surface, and then get the 2 beam, and then go to the detector. These 2 beam form the interference and form this fringe pattern. And left this pattern, and then based on this, so we can get the height information. So that is get the roughness, step height of the information. So next slide, I will talk about this. On the right, that is a real example of this fringe pattern. And this is on a silicon sample and etched pattern. So for this, form this fringe, and look at this. Maybe some of you think about and some reader, and this is on the flat surface. Why? That only focus on the center, because on the big contrast, that means focused. On the left, on the top, on the bottom, that is not focused. So that's why I'm focused here, because this should be flat. So in reality, this sample is on the stage. This stage cannot be perfectly horizontal. So always have some tilt. So you only can, if it's a perfect horizontal, that is the pattern, fringe pattern should be everywhere on the surface. This now is on the center, means only focus there. So how do you measure this on the top, on the lower part? So we use, we call the vertical scan mode, and we can change the Z height, like level by level, like this one, we can get there. Okay, so next slide, I will talk about this, and for the objective lens. We have 2 objective lens. And for the 5X, use the right, this configuration. This reference mirror is on the right. On the left, this is called the mirror object lens. This reference mirror is on the top there, inside. There are 2 configuration, and so that is for different magnification. So used for our optical profilometer. So this is for the roughness and height information. And they have a different mode to measure. For very smooth sample, you cannot adjust the height too much, because it is very smooth, just like a nanometer scale. For this one, basically we use the phase shift mode, PSI mode. For this one, you don't need a vertical scan, this change Z. It only is based on the different height on the surface, because they have a small phase shift. Based on this information, we can get the topographic image. So this only used for like less than 100 nanometer, typically like a nanometer scale, the very flat surface. The common use is the VSI mode, the vertical scan mode. This one, you adjust the Z from typically go up like a few micron, go down like 20 micron. Of course, based on your step height, you can adjust. This go like a level by level like this, adjust the V just the Z height, and then we can get the height information. So this VSM mode is common use and for our application. So next slide, I will talk about this real sample. So this sample is a silicon sample, so etched, use a chemical etched pattern. On the right, the 2D image. On the left, you can easily get a like 3D image of this. We can adjust the angle, we can get a different view for this. On the right here, the line profile, you can put a line and you can put a horizontal and a vertical, this line, and then you can get a line profile. So this, you can see R and M. So this gives you this information. The delta X is the 2 bar, the distance. So the delta Z is a step height. So for this one, we get the step height is 0.07 micron, is 73 nanometer. So that is the trench etched, how deep. And also you can see the feature at the edge. You can see there is some piled up here and give you a small feature of this. Okay, go next slide. I will show this. And on the left, that is a very smooth surface. We did the non-indentation, use our speed, the instrument. So that is a different force. You can see makes the crater is different. But after makes the crater on the surrounding area, so also that is pushed up. That is like a volcano, open it like that. So that give you a view of the after indent, how it look like. And so on the right, you can see this is a device, and device we made 2 crater. These 2 crater that is use seams to make. So our top seams and XPS both we can do depth profile. So that's very common used. But both these instruments like XPS seams, that is impossible to measure the depth for themselves, because XPS seems don't have like depth this information. And how do you get this calibrate? Typically, we use this crater after we made. We bring to our tool the profile meter and get the image. We measure this how deep that is, the height information, and then we calibrate our etch rate. So that is a crater made with the seams and how we calibrate the depth. Okay, next I will measure that. So that is another sample is a copper film, very smooth film on silicon. Based on film, you can get it on the right, you can see the analytical result. You can see get the roughness. Some sample special is wear, and that is whereas film, you want to measure the roughness, use this one, is very quick, you can get this information. Okay, so next I will show this. And this one, this view, on the left is quite normal. You see here, you can get a line profile. On the right, you can see that is dark area. On the dark area, there is no height information. So why there is no height information? So for optical profilometer, that is very common. If your sample, some is the wall is too steep, like on there is too bottom, that is too deep, like the edge. So this one because we based on the light reflection, if no light come out, so too steep on the side, and you cannot get the height information, and then so you get it like this black, the area. Okay, so next this one and is a stitching feature. So this optical profilometer have this feature. So if you want to take advantage of the high magnification, you use 50x. This get a very good letter resolution, but they also want to see a big area. How can you do that? You can use the stitching feature. And on the right, you see here, we have like 2 millimeter. We can use like a 4 by 3. Sometimes if it's bigger, maybe 10 by 10. like this. You can many image use this stitch feature. You can stitch together, see a big view, still maintain a very good and letter resolution. So this feature is very useful. So next, I will show this just like a summary for the optical profilometer. So you have a great vertical resolution and the nanometer scale. The lateral resolution can be ranged based on the objective length. You can get it down to like 100 nanometer. And high speed, that is the advantage for this optical view. You get a 3D image. They just take a few seconds. They can get a 3D. That's high speed. Another advantage is no damage because no contact. So you can, even for some like very soft, even sticky some sample, you can use this method. And not compatible with like a stylus, use contact method, but you use this one, there's no damage and can be a very soft sample, you can use this. Okay, so stitching feature, of course, is useful. Okay, so that is a stylus profilometer, and the left image is our stylus and profilometer, and on the right you can see that is a tip. This we call the stylus. This stylus is made by a diamond. The end part is made by the diamond. That's very robust, very reliable, and durable, and stud. They can use very long time. This, and the bar made by the steel, and that is they will censor by the deflection of this. So on the next slide, I will show this. On the right, you can see the image. The stylus, the scanning on the surface, basically for this, for application here, basically you move the stitch, the tip doesn't move. And you move this direction, and if you go higher, and then this tip will be deflected and get displacement. This, what sensor we use? Later I'll talk about, and for this FM we use a laser, and use optical microscope we use a light. For this one we use a tip, but the sensor not use a laser. This use a sensor called LVDT, the linear variable differential transform. This is an electromechanical sensor. So after this travel this stage and makes the tip, that is a level, that is a beam bar that is deflected. So they will generate the mechanical deflection, generate a voltage, voltage signal. And this voltage signal, and then after calibrated, and they give you the height information. So this stylus profilometer use the LVDT sensor method. On the lower part, you can see this tip, and this tip is not very sharp, and because this is diamond milled. Get this? So this angle will be also determine the lateral resolution. So this angle, if very sharp, and they can get deep and get better in the lateral resolution, but it is very fragile, like delicate. If like a big angle, yeah, very robust, you can use a very long time. Our typical use is like 45-degree that angle. So that is a radius for the stylus and the rust. And on the left, you can see, and I just show you general, this tip radius can be 50 nanometer to 200 micron. But for the below the 1 micron radius, you have to use a different sensor to use that one configuration. Typically, we have used like more than micron, this radius. Our current installed is 5 micron, this. And this one, and stylus profilometer give you data is very reliable. Why we compare this one, I said, for optical, you see, for some sample maybe can be, and it cannot measure if it's too deep and the voice too steep. But this one, yeah, always give you like reliable data. Let's see the next slide. So here on the right, you can see the profile on the line. So this is a 63 nanometer, this step height. And on the left lower corner, they basically give you this step height information. And this one you get 2 bar. And this I also expand this 2 bar. And this one is advantage. You can get average. You can just use narrow bar, maybe variable by the roughness on there. And then you can average them. On the lower, that is 3D. So this status profile meter is also available for the 3D, this mapping. But this, I said, is very time consuming because this one, every one scan, they will soft touch a surface. And then depends on your area, how big, and depends on your resolution, the gap, how many scan you want. They can take somewhere from half hour to a few hours, depends on this. But as an optical, it just take like a few seconds. So typically, our user from status profile meter node used for 3D if possible, but it's a node. Typically, it's a line profile is commonly used. Because this is a contact method on the left image, if you look at it careful, you know that is on the status. Left is real image, and on the right, the reflection. On the bottom, on the below the tip, you can see, if you see carefully, there is a scratch. And because that is and contact method, if your press force is too strong, or if your material is too soft, and they can make a scratch. Of course, this scratch will be damage your sample, will accumulate this particle on the tip. Also, the measurement not accurate. You have to be very careful, look at if that is a scratch made. Okay, so next slide, I will show some, like also can be some artifact if your feature is like this. If you have a very deep trench on the top, you can see they cannot reach this bottom, and then they give you the width, and these depths all compromised, and that is not real. So, yeah. On the bottom here, the different like feature you can see on the left, that is 200 wide and 20 micron deep. Like this, use our tip, you can get the measured surface, and the actual is very, very similar because that is very shallow. Is on the medium, this one is like 100 deep, because the deep is because the radius of the stylus, you cannot touch this corner. So you get the width of the bottom is much short, this one. That is not real. On the right, that is shrink to, and because this one, the trench is much deeper, it's 100 micron. So this tip is cannot reach the bottom. They give you like artifact like this shape. So that is a different feature. And when you measure your feature of your surface, you consider about the shape of the radius. Okay. Next slide is a summary for the stylus profile meter. And they can do 3D topography, and also, and of course, traditional, the line scan is commonly used. They can do, this advantage very large area. They can do even use stitch fixture, go to 6-inch waveform. And the vertical resolution, they claim they can do 1 angstrom if your sample is smooth enough. And this vertical scan that really is a big advantage if you have a big sample roughness and or some big step like 100 micron, 200 micron. This one can up to 500 micron. Of course, you can use FM and use optical cannot do. This one you can use and stylus because very big vertical range. So that is very easy and user-friendly. Because you use others, you have to be focused, you have to be like adjust a lot set up. This one, even you don't need to focus, just land on your sample and start. It's very quick. So save a lot of time. The stylus radius, what we have now is like 12 micron, 5.2, and typical we install is 5 micron. So this, what information you can get? Besides this step height, roughness, for this stylus profile meter, also we can get this curvature measurement. If you have whole wafer, you can get a curvature measurement. And also you can, if you do a coating on the film, you can do the film stress measurement. Okay, we go next slide is, so here, and I want to show the two results, and one use optical profilometer, one is use status profilometer, give you the difference and compare. So this is a device that is metal coated on the lithium niobate and on the SiO2 silicon. So on the surface, we have two craters. So that is, we use the seams to mate. And first we measured on this, on the right crater. So this one line profile, and on the bottom, you can see based on the optical profilometer. So we get the so that is on the bottom here, on bottom right, you can see delta Z is 1.088. Okay, 1.08. So that is the height, how deep of this crater. This is not on the red area. Red is the metal, is on the green, that area, blue. Okay, on the right, you can see 1.08. That profile is based on the status profilometer. So that status profilometer result and optical profilometer result, they are matched, they're very similar, 1.08. So for this area, for this lithium niobate, this area crater, we use two methods. Their results are very similar. But go next slide, we will show you the result is on the metal. So here I didn't measure the crater, I measured the metal. You see on the metal area, you can see this bottom is the profile. So this gives you delta Z. From the optical is 1.5 micron. So if you look at on the right, same area, I use the status profilometer, just 150 nanometer. So which one is correct? So why is the result different? The based on our common sense. So if you do the device, do the metal coating, typically you do like 100, 200 nanometer. You don't need to do like 1.5 micron. So look like that is optical, give you wrong information. So why I also trust this status profilometer, not just by common sense. You know, the status profilometer is direct measure use tip. Sometimes they give you some error if your surface is rough, you have a roughness. But because this direct measure, they cannot generate a huge error. So that is status profilometer result always like reliable. On the left here, they give the big reference. Why is generated this? So next slide, I will show you this. They code like a dissimilar material use optical profilometer. So they measure this based on the phase shift. Okay, the light reflect on the surface, and then they will generate the phase shift. This phase shift based on the optical constant N and K, N of refractive index, and the K is extinction coefficient based on this. And you see here, if you same material, okay, this is, if it's same material is flat, and then this phase shift is same, okay, these give you same height. If it's a different height, and they will give you based on the phase shift, give you the height information also accurate. But if this phase shift not just caused by the height, also caused by the different N and K. So this one, that give you the height information also wrong. So that's caused this error. So for different material, if on like last slide, there is lithium niobate and the SiO2 on the crater. So Z2 material NK, not a big difference. And then give you the height, it's very close. But for the gold, for the metal, and the lithium niobate, these two materials, especially gold, the extinction coefficient very high. And their NK is a huge difference, the two material, and then give you the huge error. And so that's why, so they give you that. So when you use optical profilometer, if it's a different material, you have to be very careful for the height information. If their NK is a huge difference, can generate error. But if it's the same material, you want to measure roughness. If same material, you want to you etched some like a trench, that is totally no problem for that. Well, of course, this an offset, we can use method to correction, but that is a lot of calculation for that one. Typically, we use the status profilometer, we can use it to measure, but that is a method you can make a correction for this offset. Okay, so next slide, I will show you that is a third method for the topography. It's called FM, some also called SPM, scanning probe microscope. So this left, the icon is our system in the spit. And on the right, you can see this, the tip, the touch on the surface, and then this vibration here. And then on the top, that is cantilever, and use a laser to reflect on the surface. And then use a photodiode to detect the deflection and the displacement. And then you get this topography. And for this one, and the cantilever is always like resonant at the frequency. And the amplitude is maintained the same. They use a piezo to make up down there. Okay, so next I will show you this is 3 different mode for FM commonly used. So that is contact mode, non-contact mode, and tapping mode. Contact mode is like our status profilometer, always contact on surface, make contact. So this one is can be damaged on the surface. They can get the highest resolution, but that is can be damaged. And also the tip easy to wear. So you have to be, probably every time you have to be replace the tip. Okay, so on the right is no contact mode. It's always keep our distance. For these ones, attractive force to make them and use the no contact. That is no damage on the surface, but the resolution relatively is low, especially in the air. So that is a resolution very low. So that is, I know that is in the ultra-high vacuum FM, they typically use this because that is in the ultra-high vacuum, they can also get a very high resolution of the lateral resolution, vertical resolution. Okay, most often used in our system is called the tapping mode. This intermittent contact on the surface. And like this method is a combination, and for these two, and this is no damage on your sample, is also very high resolution, lateral and vertical resolution. And your tip is can use many times for this. Okay, so next. So here shows that that is like a very well known as a potential, and depends on the distance. This graph. On the left, this is the contact mode, is a repulse force. This very contact, touch the surface. On the right, if you have keep distance, there's attractive force. Tapping mode basically between on this touch and the and keep a distance like this change. So that is where is the tapping mode should. The tapping mode is this developed tapping mode is very good for the fragile sample. They also can get a good resolution, and then they can compatible with soft material for this. Okay, we can go next. So here left is shows that what is the FM tip look like. And before I show you for the status profilometer, that tip really is a big angle and also use a diamond. That use a diamond and made the tip. They're very sturdy, very like durable. Typically, the stylus we can use like a year, 2 years. We don't need to change. And so this tip, of course, it can very sharp, use fabrication made, and they can get a very good like lateral resolution and water resolution. But this tip, you like radius from 1 nanometer to 20 nanometer, they only can use a few times. You know, if you use FM, maybe you frequently have to know how to change the tip and a new tip. And also on the right, you can see here that is a 2D material flake like tungsten sulfide, and the hybrid that is a structure, header structure. And then you see the height information is a 1 nanometer. That is a line profile. This is very accurate for the vertical resolution. On the right, you can see the two image, the small particle like zinc sulfide nanoparticle here. The lateral resolution also very good. So this. Okay, we can go next. So why is this the different use both the three all three methods, their vertical resolution, all they are getting 1 nanometer, even that is for the FM they can get it angstrom the resolution. But the lateral resolution is a huge difference. Use stylus profilometer and the optical, they get like much bigger, and the micron even 10 micron, 20 micron. But use FM, use that is a nanometer scale. Because you FM, they use a piezo stage. The XY, they move, they use the piezo. So this advantage is very accurate for the lateral resolution. But the disadvantage is the range. The piezo, they cannot move too much. They cannot move too much. So only probably maximum like 60, 80 micron, it cannot go further. And on the right, here we use a motorized stage. So that's why we can use stitch. We can measure like a few 10 millimeters, they go much wider range. But because this use a motorized stage, so that is a lateral resolution is poor. Okay, so next I will summarize this and 3 different methods. Stylus profilometer, and very fast, very easy, and no setup, focus time, and don't need to change tip. And you just very quick put your sample, the length, you can get in a few minutes, you can get the height information. And this also is a huge vertical range for big sample, big step. You can use this and also get a great vertical resolution. But this weakness is a poor lateral resolution. This also, there is a contact mode, and they can damage the soft surface. If you do 3D, use this method, time consuming. Okay, the 3D optical method, this also fast and easy. And this is a better lateral resolution, no contact. Okay, great vertical resolution. So this one is special. Okay, not yet. And then not work for the low refractive surface, especially the if can be have an artifact if dissimilar material on the surface. So FM method, that is the best, give you always the best lateral and vertical resolution. It's great for the atomic layer film, like a graphene, like that one you always use, like this FM. It's great for soft material because we use tapping mode. But disadvantage is XYZ, this range is limited. You cannot scan big area. If you have a big bump on the surface, the big sphere, you cannot use FM to measure. Also, the tip is easy to wear. You have to replace the tip very frequently. Okay, the setup, of course, every time you need a tuning this tip and also take time. Yeah. Okay, so next slide is the last. I want to see where they are and the face, and the horizontal is the lateral range, and left is the vertical range. You can see the all 3 methods. They are vertical is the range that is 1 nanometer. That is very similar. On the vertical here, and the FM that is on the left side, a stellar profilometer on the right. That is, you can see the big range and for the lateral and sample. So optical profile mate at the middle of there. So that is where they are. Okay, so that is our talk about these 3 different methods. And if you have any question, and you can talk. I don't know if somebody put it in the chat or maybe you can talk. Okay.